Namaskaram. Math, like life, is a story. So let me tell you a quick story. Now, here I have a rectangle. So I'm going to draw my rectangle like this, and like this. Now, the length of my rectangle is 5 meters. The breadth is 3 meters. So we have 5 meter by 3 meter rectangle. Now, in math, we have something we call area. Now, in simple English, what does area mean? Area simply means I want to get some kind of a number, some number to accurately show or give me an idea of how much space there is on this plain rectangle. Just a number to show me how much space there is. That's basically what we mean by area. So the question is, if I need a good number to properly represent how much space there is, this number must also work in all cases, which means if this space increases, if the rectangle becomes bigger, same way that number should become bigger. If the space becomes smaller, that number should become smaller. So this number must be related to the space in some way, then I can call that number area. So how do we define this quantity called area physically? What we can do in order to get this number is, one way of doing it rather, I have this length 5 meters, I'll keep that fixed. What I'll do is, I will take this 3 meter breadth, okay, and I want to get some idea of how I can cover this entire space. So I can think of this entire space as taking this line 3 meter and almost going like a typewriter, stacking this line again and again and again and again and again, and all the spaces in between as well, going all the way from here up till the end. So stack, 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 stack. Once I do that, if I can find out how many such 3 meter lines are required to fill up the entire space, if I can count that, that will give me a good idea of how much space there is. So I can think of the area is that much space that is filled up when I take this 3 meter line and do a stack, do a stack across the entire length of 5 meters. So that's what we're going to try to find out now. How many such 3 meter lines do I need? Now it's a weird question because the thickness of each of these lines, each of these 3 meter lines is just a line. There's no real thickness, right? It's basically 0. So how many lines can I fit in here? Well, can I fit in 100? Actually, I can fit in 100 just in a space from here to here, because in this small space, how many points do I have? I have 1 million, maybe 2 million points, infinite number of points. From each of these points, I can draw lines, right? So the number of lines that I can fit in even in a small space is actually never ending. So which means if I have to fit this entire space with lines, 3 meter lines, the answer would be actually never ending, because each line is of 0 thickness and there are infinite points here. So the answer is not 100, it's not 1 million, it's not 2 million. So what do? We can think about it in a different way. Let's say I just draw 5 lines. So how many what's the total amount of space that I have covered? I have 3 meters per line and I've drawn only say 5 lines. That will be 3 meter plus 3 meter plus 3 meter plus 3 meter, 1, 2, 3, 4 plus 3 meter. This much total space has been covered. So a short way of writing that is 3 meter into 5. But of course, 3 meter into 5 doesn't cover the entire space. It's just 5 lines. It will cover a very small space in this rectangle. But we know we want to cover the entire space. And we know that if I want to count the number of lines here, that will be never ending. That will be infinity. So now we have to think about this in a different way. We can use this multiplication as a clue. We're not actually doing 3 meter into 5, because 3 meter into 5 will just be adding 5 3 meter lines. But what we are trying to do is actually to cover this entire area. We can take the clue from here. We're taking this 3 meter line and we're adding it not 5 times, but we're adding it 5 meter number of times. So 3 meter, 3 meter, 3 meter, 3 meter, 3 meter, 3 meter, keep adding it. How many times? Not 5 times, not 100 times, not 1 million times. We are adding it 5 meter number of times. That many times. That means we are adding 3 meters for a length of 5 meters, every point. That will cover the entire area. So the area therefore becomes a product of the breadth 3 meters and the length 5 meters. This actually tells you the story. It tells you that the amount of space in this rectangle is the amount of space that you get when you take this 3 meter line and you stack it for a total length of 5 meters. Therefore, this is a good formula to show us and give us a good representation of how much space there is in this rectangle. Therefore, we get our famous area formula. The area of a rectangle is its length multiplied by its breadth, and this will simplify to 3 meter into 5 meter, 15 meter square. So when you see 15 meter square, physically what you think about it in real life is 15 meter square means it tells you that you're talking about a rectangle whose space is how much? Is that much, which ensures that you can take a single 3 meter line and stack it across a length of 5 meters. How much of a space that's covered there? That is what 15 meter square is. So this is basically a physical way of thinking about area. It's not the only way, but it's one interesting way. And that gives us our fundamental formula of area of a rectangle, length into breadth. I'll write that here. Area is length into breadth. Just think of stacking and covering the entire space. Now, here's where it gets a little bit tricky or interesting. This area, length into breadth, believe it or not, whether you're talking about mathematics at grade 5 level or PhD level, this is our only formula for area. A plane surface, if you want to find out the amount of space there is, that means the area, this is the only formula. So the question is, okay, this works for a rectangle. How do I use this formula to find out the area of other shapes, triangles, circles, other kinds of parallelograms or whatever it is? And then finally, what about a completely uneven surface, right, which is not a regular shape? How do I find the area here? If our only formula is length into breadth, how do I use it for other shapes? That's an interesting question. Okay, so now that we know our basic area formula, which is the area of a rectangle, length into breadth, how do we now use this formula to find the areas of other shapes? Let's take, for example, a triangle, and I'm deliberately going to draw a triangle which, my drawing skills are pretty appalling. I'm going to basically think this is a triangle. Okay. So this is a scalene triangle, just to make sure that we have the most awkward and weird case. Scalene meaning no angles are equal, no sides are equal. It's not isosceles, it's not equilateral, it's just a random troublesome triangle. We want to find out the area of this triangle, which means we want to get a number which is a good representative of how much space there is inside this triangle. And remember, our only formula is area of a rectangle, stacking and covering the entire shape, length into breadth. How do we use that here? What we're going to do is we're going to somehow try to think of this triangle in terms of being part of some other rectangles. What do I mean by that? First thing I'm going to do is I'm going to draw a straight line down like this, and I'm going to draw it perfectly, kind of making a T with the base, which is basically in mathematics what we refer to as a 90 degree. So basically this line is a good measure of the height of this triangle because it goes straight down, even though my drawing might not make it seem like that. I failed in my art class, not my math class. So this is what we call a perpendicular. So I'll put this point as P. So AP is actually the height of this triangle because it's a perpendicular. This is going to help me a lot. Now I want you to just focus on this side of the figure. I have this triangle, the smaller triangle here, APC. What I'm going to do is I'm just going to complete this figure. Just like PC, above I'm going to draw another line. Exactly like PC or parallel to PC. And parallel to AP, here I'm going to draw another line. Maybe we can call this point Q. And now if you see, something interesting happens. This triangle APC is like a mirror image, or it's basically the same, a flipped version of triangle AQC. And this line AC is functioning as like a mirror. this triangle and this triangle are exactly identical because this has become here and this has come here, 90 degree, 90 degree. And now you see something interesting. The figure AQPC is a rectangle, 90 degrees everywhere. This is a rectangle, and this is a rectangle which is split into two identical or equal triangles, which means if I find the area of this rectangle using our length into breadth formula, divide that area by 2, take half of that area, that will give me the area of this triangle APC, just this much. That's the first interesting step. Just like I did that here, I can do that here. Just like side PB, above here I can draw a dotted line, and just like AP, I can draw another dotted line, and just like I got a nice big triangle here and two identical triangles here, I can do the same thing here. A rectangle, a nice big rectangle, I'm sorry. I have a rectangle here, and this rectangle is broken into two identical triangles. One of them is the other part of this big triangle, ABP, and the same mathematics that worked here will now work here. If I find the area of this rectangle, maybe we can call this point R, ARBP. If I find the area of this rectangle, take half of it, that will give me the area of this triangle. And now we get the area of the full triangle ABC. And how is that? Half of this rectangle will give you this, half of this rectangle will give you this. So you add up this and this, now you get the area of this full triangle. Let's try to do that. Let's do this one first. So basically, I'll call this height AP, I'll call this height H, H for height, okay? AP is basically H. So now basically let's do that. So in this triangle, in this rectangle, rectangle ARBP, the length is BP and the breadth is AP or H, and we're going to take half of that because we don't want the rectangle, we only want this particular triangle ABP. So we'll do that. So the total area is now equal to half of length into breadth, that is BP into height. Height in this case is the breadth of this rectangle, right? That is that. Now this half BP into H will give us this area, because it's half of this rectangle, it's this area. Same way we'll do that here. Half of this rectangle area wise will give you this, right? And what is the length of this rectangle? PC. What is the breadth of this rectangle? It's the same, QC, AP, RB, all the same, which is basically the height of the triangle H. So that is plus half into PC into H. You add these two up, you're getting half of this, which is this, and half of this, which is this. Adding up that is the full area of this rectangle. Let's simplify that. I hope I have enough space on my board. Now, if you are familiar with a little bit of algebra, half into BP into H plus half into PC into H. So if you see in these two terms, there is a term half into H, which is actually common, right? You see this? Half into H is actually common. So we can take what we call as a common factor, okay? We can take it out. This is what we call as factorization. So half into H is common, and that multiplies by BP plus PC. If you have a doubt as to how that happens, you can actually open it out again. Multiply this with BP, you will get back this. Multiply this with PC, you will get back this, right? So now I have half into H into BP plus PC. And now we come to our formula for the area of a triangle, because now I have half into height. And what is BP plus PC? BP plus PC is actually the total length of the base of this triangle BC. I can write that here. BC, I'll call it base. Base means B is equal to BP plus PC. BP plus PC. So I can replace BP plus PC as the base of the triangle. And now we get our next famous formula that you've seen in many textbooks. The area of any triangle. I'll probably write it up. As you can see, you know why I failed art class. I'll write it up again, or maybe I'll write it here. Area of any triangle can be got by half into its base into its height. So now we can see again, we just used our length into breadth rectangle formula and we converted our triangles by thinking of them as part of other rectangles, and we get this golden formula. Area A is equal to half base into height. Now we're not done yet. Our last one for this small little exercise is we got rectangles, we got triangles. Now the question is, if I give you a circle, you can imagine how bad my circle drawings are. If I give you a circle of radius r, now I want you to tell me the area of this circle. Now it gets funky. So now we have our next problem. How do I find out the area of a circle? Now the proof that I'm going to show you towards the later part is something that I have sort of winged and come up with on my own. I haven't seen a version of this in other places. So it's a challenge to you also, the viewer, to check this and tell me if it's legitimate, because all the other proofs for area of a circle use something that we refer to as calculus, which is a great method, but I have tried to find a way to do it without that. So you be the judge and call me and let me know if I'm on the right track or not. So we'll get there. Area of a circle. Before we get to area of a circle, we need to know something a little bit more about circles. So let's look at that. Now if I ask you to draw a circle, typically what you're going to do, you're going to take your compass, put it on your scale, find out a certain distance, put that compass on the paper, and then woo, and you draw a circle, right? So let's try to do that. Please, I apologize for my crappy circles. So we're going to basically take our compass, put it here, and then we're going to draw a circle. Okay, not too bad, right? Now, the speciality of a circle, even though my circle doesn't look like that, but an actual circle, is that every point on the boundary of the circle is located at the same distance from the center, and that distance is what we call the radius of a circle, right? So all the points are located at this distance r. So this is r, etc. We get a kind of a chakra basically, right? That's the beauty of a circle. So this distance, the distance between any point on the boundary of the circle and the center, is what we call its radius. Now I can extend that. I can take for this point here a point which is exactly opposite to this point on the other side of the circle, which is therefore also located at a distance r away from the center. And now I get this line. This is a special line for a circle, basically because it joins one point on the circle to the opposite point on the circle through the center. And this line is special, this line is special because it divides the circle into two equal parts. So the area of the top part is exactly the area of the bottom part. This length, let me call that AB for example, is what we call the diameter of the circle. And from the figure, it's quite clear that the diameter is basically made up of r plus r, right? And we don't have to draw the diameter only here. I can do it here also. In any direction, it will divide the circle into two equal parts. That's called a diameter. And if you look at the mathematics of it, the diameter d is basically r plus r. In other words, d can always be written as 2r. So in any equation, if I have d, I can replace it by the term 2 times r, 2 times double of r. Okay. Now, the third important point about a circle is what we refer to as the perimeter of any figure. What does perimeter simply mean in English? It means that if I'm standing here and I'm not interested in the space inside the circle just yet, I just want to find out what is the length or what is the distance that I would have traveled if I go along the boundary of the circle, just along this red curve, right? Along the boundary, and if I go like this and I come back here, what is the total distance I would have run or I would have walked? In other words, what I'm asking you is, if I take a pair of scissors and I cut the circle here and I only take this outermost boundary, make it into a straight line, measure it with the ruler, what will the length of that line be? In other words, we are talking about the boundary of the circle. Perimeter is what we call it, right? And for the circle, we give that perimeter a special name. We call it circumference, C. So when I say circumference, again, not very good at sport. When I say circumference, I'm talking about just the length of the outer path, not the area inside. Okay. Now let's think about it in terms of how these are all related to each other. What do you think will be the connection between R, D and C for different circles? Now we can imagine this, right? If I draw a bigger circle, how do I draw a bigger circle? I'll have to take a bigger radius. So maybe I'll start from my center here and I'll take a much bigger radius. So let's say this is much bigger than this, and if I draw it, I'll get a much bigger circle. Apologies again for my circle. This is a circle. This is a much bigger radius. If the radius is bigger, obviously 2 times the radius, the diameter is also bigger. And you can see now that the circle itself becomes bigger, right? So not only is the area more, because the circle is bigger, the length of the path that you have to travel around the circle, which is basically the circumference, right? From here, it has now also become bigger. So if we want to put this whole story in a simple, succinct way, we can say that as the radius increases, as the radius becomes bigger, what will happen to the diameter? Diameter is twice radius. Diameter will also become bigger. And as this diameter becomes bigger, what happens? The circle itself is bigger. So that means the circumference, that is the boundary, the perimeter, also becomes bigger. Of course, the area also is more. We'll come to that. I'm more interested right now in these 3 terms, R, D and C. And the same thing can happen in reverse. Circle gets smaller, R becomes smaller, D becomes smaller, C becomes smaller. Now let's try to get more specific, because mathematics is all about getting specific relationships, right? I'm going to look at these 2. So I know that as D increases, C increases, and therefore as D decreases, C decreases. But is there a very specific mathematical relationship between D and C? You know, something that can allow me to predict C if I know D, or predict D if I know C. Now you can do this experiment. It's actually a pretty crazy, fun experiment. And I'm going to give you the results of it in summary. But if you can take any circle in the world, from the smallest circle to the biggest circle, you can do this experiment at home. And for each such circle of different sizes, you can measure their values of diameter. You can note it down. You can measure the circumference C and note it down. And you will find something astounding. And the Greeks were the first to discover this, that for any circle, no matter what the diameter is and what the corresponding circumference is, there is a magical relationship between C and D for all circles. And we found out that for any circle, C divided by D will always be equal to this magical number, 3.14. Of course, specifically there are many more decimal digits. We'll take it as 3.14 for now. This is an astounding result, because this tells us something universal, right? That for any circle, from the smallest to the biggest, the ratio of circumference C divided by diameter D will always be a little more than 3, which means for any circle, the circumference is about 3 times the size of the diameter. Therefore, this is a special number, which it's a very famous number, obviously. So we call this pi. The reason we actually call it pi is because the Greeks were the first to kind of work on this, and for them in the language, Greek language, perimeter starts from P. The first letter in Greek was pi. And since we're talking about circumference is just perimeter, right? So that's where the word pi comes. It refers to perimeter of a circle, and the letter for P in Greek is pi, right? So this is a very important relationship, and now we get this in mathematical form, and we can write it as C by D is equal to pi. And this is quite an amazing relationship, because it works for any circle anywhere in the world or in the universe. Now we are getting ready to talk about the area of a circle, because that was our original problem. Now is the grand finale. Let's see what all we have figured out so far in a very kind of real, visceral, organic way. We know that the area of a rectangle, which is basically the only area formula we have, stacking, right, is its length multiplied by its breadth. Using that, we were able to figure out the area of any triangle as half multiplied by its base multiplied by its height. And then our last part, what we saw was for any circle, the ratio of its circumference to its diameter is a special number pi. Now using these three and nothing else, we are going to attempt, remember this is my weird proof, so you got to check and tell me if it's legit or not. We are going to try to attempt to find out the area, that is the space occupied inside a circle, inside a flat circle, the area. Before we do that, let's rearrange this a little bit. Instead of saying C by D is equal to pi, another way of saying the same thing is I can bring the D to this side, division on one side becomes multiplication on the other. So I can say it is pi D. And you also remember that the diameter D is equal to twice the radius. Diameter D is twice the radius. So in this equation, C is equal to pi D, I could replace D as 2r. Pi into 2r, which means I can basically, if I put this a little bit on top, I can say C is equal to 2 pi r. This is quite a useful relationship, as you can imagine, because if I know the radius of a circle, I plug it into this equation, it tells me that the circumference is about 2 pi times, not about, it is 2 pi times the radius. 2 pi approximately is about 6.28, which essentially tells you that the circumference of a circle is about 6.28 times its radius. This is about 6.28 times this. So we're going to use these equations now, all of which we've derived in a very clear way, to now try to find out the area inside this circle in our crazy way. Let's see what we can do. So here I have a straight line. This is just like the ground itself, just a straight line. And resting on this straight line is a smooth circle. Please assume that this is the smooth circle. We've spoken about my art skills, right? The center of the circle is O. And if you're able to visualize this, a circle is a smooth curve. So because it's a smooth curve, it actually will rest on this line, a straight line, only at a single point because it's curving continuously. So when it curves continuously, if you rest a perfect circle on a straight line, the contact between the circle, which is curving like this, and the line is actually just a single point. Even though my diagram might not make it seem like that, it's actually just a single point here. Right? And this point is also on the circle. So if I drop a straight line from the center of the circle O to this point, that is the point where the circle touches this line, that point is basically on the circle as well. So this is also the radius, right? Maybe we can call this point P. So OP is the radius because it's a point on the circle. And also, if you look at the line OP, it just goes straight down. It basically meets this line at a kind of a T, which is basically what we refer to as 90 degrees or right angle, right? Which means this R, which is not only the radius of the circle, it also is the height that the center O is above this horizontal line. It's a height because it's straight up, it's not slant. If for people who are familiar with a little bit more mathematics, there is a rigorous proof for why this line will be exactly at 90 degrees, because this line becomes what we refer to as a tangent. More on that later. All right. So now we know that this OP, which is the radius, is also the height of O above this line. Now we're getting ready. Now I want you to use your imagination here, because our aim is to use all this stuff to find out the area of this circle. Now, before we go ahead, I want you to imagine this circle as a whole bunch of smaller circles stacked up together. What do I mean by that? This is the outermost line or circumference, right? But this entire space inside, instead of just thinking of it as a big blocky space, I can think of it like this. A circle like this, whose center is again O, then an inner circle like this, whose center is again O, and I can keep going, right? I can get circle after circle after circle, all the circles centered at O. We use the word concentric. They all have the same center, like an onion, you know, smaller circle, smaller circle, smaller circle. So basically, the entire space that area that I want to find, I can now visualize it as several circles of smaller and smaller and smaller radius, and therefore of smaller and smaller and smaller circumference, all centered on the same point O, and that covers the entire space. How many such circles are there? I have only drawn a few, but they are actually infinite because the thickness of each is basically 0, right? So now if I think of this entire circle as several concentric circles packed in, I have covered the entire area. This is going to be useful for us. Now, what about the outermost one? The outermost one is the red one. Now, the length of this outermost one will be 2 pi times the radius of the full circle, right? The length of the inner circles, I don't know. The circumference of the inner circles, I don't know. I only know the circumference of the outermost one, which is the one which is not put in the dashed one, which is the full one. The other ones are all dashed. They are all smaller radius, smaller circumference. I don't know what their values are. I only know that if this full circle's radius is r, this outermost guy, circumference, is 2 pi r. Everything else, all the inner circles, the total perimeter of those inner circles will be obviously less than 2 pi r because they are inside. I don't know what they are. I don't need to know also, and I'll show you why. Now, we're going to try to find the area. Here is where our imagination comes in. Imagine now, close your eyes if you have to, that you have a pair of scissors. And we're going to do this very careful SUPW work now. We're going to take our pair of scissors and we're going to make an incision, a surgical cut, only on the outermost loop. That is only on the one which is in full red, not dashed. I'm only going to cut this exactly above O. So exactly above O. So that means half is this side and half is this side. Not the inside part, just the outermost one, the outermost ribbon, just cut it. When you cut it, what's going to happen? This half will fall on one side, it will fall this side, and this half will fall this side. Only this. The rest of the circle is still sitting like that only. Only this outer part will fall here, half. The other half will fall here. So that diagram, I'll show it over here just so that you can kind of separate them. The same point O, the center I've drawn here. The same height, which is basically R, I will redraw here. That is this point. This is P. Same point. Now what's going to happen? When I make the first cut, this fellow will fall this side. So maybe we'll call that point, what do we call it? We'll call it B. And this fellow, just the outer guy, will fall same distance on this side. Maybe we'll call him A. Now what is this total distance? The total distance of this straight line AP plus PB, that is AB, they're actually equal. It doesn't look like that, but they're equal. This total distance is nothing but this distance, right? It is this outermost circumference. And what is that? That is 2 pi r. And because half of it will be this side and half of it will be this side, this AP is pi r and this PB is the other pi r, which means this total is the circumference 2 pi r. The circumference is now being stretched out into a straight line. That's all. Now what is left inside? All the inner circles are still left, right? Now we'll continue the same process. Take our scissor, go inside, cut the next circle. When the next circle gets cut, again half is this side, half is this side. So half of it will fall this side, the other half will fall this side. But that circumference, that length of that inner one will obviously be less than the original one, because the original one is the full outer one, 2 pi r. The inner one will be slightly less. So when it stacks up, maybe it will go from here to here, or here, and it will stack up like this. Now if you see where I'm going with this, continue, bring your scissor down, 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 down. With each circle open out, half goes this side, half goes that side, half goes this side, half goes that side. So you're opening out these rings into straight lines, right? And of course there are infinite rings, infinite straight lines. The important point is the outermost one is 2 pi r. As you keep cutting the inner ones, you'll get equal length here, equal length here. But the lengths will start becoming smaller and smaller and smaller. So you will get something like this, right? Da 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 da, and finally you'll be left with just the center point. Which means, if you are now following my train of thought, when you open this out without changing anything, just changing where the points are, half will come this side, half will come this side, they will build, and you will basically get a triangle, right? And all those inside circles opened out into straight lines are all inside. And this is O, this is P, and if you can see, this distance from O to P is the same as what it was here, same 90 degrees. Nothing, all that hasn't changed, which means this OP is still R, right? So now what we have done is we have converted, without squashing the circle, without stretching it, we have converted this circle into a triangle. And what are the features of this triangle? The base of this triangle is 2 pi r, the outermost guy. Then inside they go in, reduce, they go to the tip. And what about the height of this triangle? If you can see, the height is basically this. Whatever it was here, the same thing is here, which means the height is just OP. The height of this triangle, 90 degrees here, the height of this triangle is actually the radius of the circle R. Now, its closure, tension has released, because now I can use my formula here, half base into height, and I can find the area of this triangle. Now, all the points of this circle are here. So, if I find the area of this triangle, it's basically the area of the circle, because every point over here comes here. So, all the space occupied here is occupied here. So, the area of this triangle, what do we call this upper points? We've already called it O, I'm sorry. AOB, right? The area of this triangle is the area of the circle. And what will that be? Half base into height, half into the base, 2 pi r into the height, r. Now simplify, half and 2 cancel, pi r into r, and we get the other hallowed formula that we all know, right? Now we know where it comes from. The area of any circle A is pi r square. Now, this is my own weird version of this proof. I haven't seen this proof in other places, so please fact check me. I've broken my head on this, so I think it's okay. But this is the proof that actually doesn't require any advanced mathematics, aka calculus. So it has a good chance of being something that is not a source of great stress for students. That's basically it, and we can continue and do many other things. I'll leave you with one question, and if you want to know the answer to that question or how to get to the answer more interestingly, you can give me a call, number in the description. Now we got the area of a rectangle, triangle, circle, but all these are still regular figures, right? My question to you as a take home is, instead of all these nice regular figures, if I give you amoeba, you know what amoeba is? Amoeba is, single-celled organism, any shape. If I give you a random shape like this, now there's no radius here, there's no length, there's no breadth, there's really no base or height, it's just like that, right? If I give you this and I say, tell me this area A of this entire space inside this amoeba, how do you do it? And remember, like we saw till now, we have only one formula for area, which is what we started off with a rectangle, length into breadth. That's all we have. We have to use that only and use our imagination and our creativity to find all other areas, whether it was a triangle or a circle or now an irregular figure. This is where it gets even more interesting. The story continues, and for that, give me a call. Namaskar.